All right, guys, how we doing? Moving right along here. This is going to be the beginning portion of essentially what's the first lecture video for chapter 10 here, or chapter 11. So let's get right into it. This is going to look kind of familiar to a couple of you guys. This word here, atmospheric pressure, right? It's essentially the amount of pressure the gases in the atmosphere exert on the Earth's surface, right? So this is a very, very big picture here, guys. I think of all the gas particles that are essentially in Earth's atmosphere. Those all have essentially amount of weight that gets applied in terms of a pressure on us, on buildings, on everything that's on the Earth's surface here, right? So again, one of the things I mentioned to you guys in class the other day was that all gases have some amount of mass to them. Again, it might not feel like it's a lot of mass, but when you've got all these particles from, essentially Earth's surface all the way up to the very, very top of Earth's atmosphere, all of those particles have a certain amount of mass then, and then therefore, because there's all that mass there, it exerts a pressure, a downward pressure on the Earth's surface. Now, what that ends up looking like is that atmospheric pressure can have a couple of different measurements, right? You can measure atmospheric pressure at a given time, okay? It's going to have a couple of different measurements, though. It's going to have a measurement of 1.00 atm, and atm is going to be called atmospheres, so that's a unit, atm, or atmospheres. Another unit that pressure can be measured in is kPa, or kilopascal. And atmospheric pressure can be measured in this unit of kilopascal to be 101.3 kPa. Now you'll also notice there's two more there, 760 mmHg. This is just a basic way of saying millimeters of Hg, which is the element of mercury, so millimeters of mercury. There's also torr, T-O-R-R. It's also measured at 760 for what atmospheric pressure can be. Now, all of these measurements here, 1.00 atm, 101.3 kPa, 760 millimeters of mercury, and 760 torr, they're all equal to each other, right? Just like every other unit equality we've talked about in the very, very, very not so distant past, right? A lot of what we covered in chapter 6 there was talking about unit equalities, right? Taking a unit equality and saying, hey, if I've got 1 foot of something, that's the same thing as if I got 1 or 12 inches of it, right? So again, it's the same thing. We're just comparing different units of different measurements, okay? But again, ATM and KPA, atmospheres and kilopascal, are going to be the ones that we focus the most on in this class here, okay? Now, how do we do that? How do we actually make these measurements of pressure, right, on Earth's atmosphere? Well, we do it using what's known as a barometer, and that's essentially the image we see in the bottom right-hand corner here. It's a tube used to measure atmospheric pressure. That's why whenever you're reading certain different things on your phone in terms of the weather app, or maybe you're watching the weather channel, or you're watching the news and the weather's on, you might hear a meteorologist, or you might read something talking about barometric pressure, right? That's essentially just atmospheric pressure that is essentially measured by a barometer. So barometric pressure is the atmospheric pressure in that given area measured by one of these barometers here. Now, speaking of pressure, we've got something here called Dalton's law of partial pressure. This is a very, very basic formula that, again, just uses everyone's favorite type of operation, and that's going to be addition here, right? So it takes the sum of all the mixtures of gases and all the pressures of those gases in the mixture, right? So the total pressure of a mixture of gas is equal to the sum of the pressures of all the gases in that mixture, right? So when I say the sum, I mean, of course, the addition of them. So what ends up happening here, guys, is that for every gas you have in a self-contained container, that individual gas exerts a pressure on that container. And if you add up all of the individual pressures that those gases exert on the container, add them all up, that's going to end up being the overall pressure that all of the gases collectively exert on that container. So this is a very basic formula to show that. Now this particular formula is very, very dependent on the number of gases you have, right? So at the minimum, at the very least, you need at least 2 gases, right? So your formula is dependent on how many gases you have in that container. So for example, if there are only 2 gases in your container, well, you only have to calculate the individual pressure and determine the individual pressure of gas number 1 and gas number 2, add those up, and that's the total pressure. That's the total pressure of both of those gases combined. Well, now what happens if you've got a third gas in your container, well, you just have to add P3 into the mix here, right? So if there are 3 gases, use P1 plus P2, and now plus P3 as well, okay? And add up those partial pressures to get the total pressure in the container. Well, just like the previous one here, what happens if you suddenly have 4 gases? Well, same deal, guys. Add P4 to the mix here. So the partial pressure of P1, P2, P3, and P4 for those 4 gases, add up the partial pressures of each gas, all 4 of them, add them up together, and now you've got the total pressure of the entire amount of gas of all 4. Now, gases, not only do they have pressure, but they have temperature and volume, right? So this is going to kind of complete that trifecta of the 3 different variables I mentioned in class, right? There's that sentence from this slide right here, and go back a couple of slides here. There's a sentence right here where gases exert pressure, have a temperature, and occupy a volume. And it was these 3 words here, pressure, temperature, and volume, that I said are so vitally important to understand and know, right? So our goal here is to track and determine and see what happens to gases when we change pressure, when we change temperature, and when we change volume. And that's essentially where we are headed here. So let's make our way back to where we just were talking about not only certain gases having pressure, but also having temperature and volume. The amount of space a gas takes up, of course, is its volume. So depending on how big a container that you've got is with a gas in it, the volume of that container is going to, of course, then be the volume of that gas. Because as we know, gases take the volume of their container, right? On top of that, gases also have a temperature because, as we know, I'm going to say this until I'm blue in the face, temperature is a measurement of the average kinetic energy of that gas. Okay, it's a measurement of the average kinetic energy of a gas. So if these gas particles are moving, they have an amount of kinetic energy that can then be translated into being that gas's temperature. So they have a volume and they have a temperature, right? And of course, you're able to determine that temperature and always translate between Kelvin and degrees Celsius if needed, right? Again, knowing and understanding the fact that if you ever need to do that translation, right, figuring out how much you have in Kelvin versus how much you have in degrees Celsius, we just have to use that lovely number of 273 to help us out with that. Okay. Boyle's law. Okay, this is the next thing up here, right? Now, we're going to be talking these next 3 slides here about different relationships between any of these last 3 things I've talked about, right? Pressure, temperature, and volume. So we're essentially going to do our best to keep one of these 3 things constant here, right? That's the main goal here. So if we're looking at a volume and pressure relationship, right? Boyle's law being a pressure or a relationship between pressure and volume. That means of the 3 things here, we're going to keep temperature. As the thing that's constant here, and change our pressure and our volume and see what happens, right? So the pressure of a gas is inversely related to its volume. Well, what does that mean, inverse? Well, if you're thinking back to math class here, that's a basic way of saying, hey, if there's an inverse relationship between these 2 things, pressure and volume, that means that as volume decreases, pressure is going to do the opposite. It's going to do the inverse. Pressure is going to increase. And this is essentially what the graph is going to look like. And I want you guys to do your best to copy down in exactly what this graph is, right? So make sure you draw your y and your x axis like this, label the x axis as pressure, label the y axis as volume, and make sure you copy down this orangish looking line here again. So as we see here, as our pressure is increasing here, we can very clearly see our volume is heavily decreasing and going down, right? So that means that in that case here, we have an inverse relationship. Now, the next here is going to be called something known as Charles' law, right? So if you've got Charles' law, that means we're relating 2 things, in this case here, volume and temperature. That means we're not worrying about pressure in this case here with Charles' law. We're just worrying about volume and temperature and their relationship, okay? The volume of a gas is then directly related to the temperature of a gas. Well, directly related, what does that mean? If 2 things are directly related to each other, again, thinking back to some relationships you guys would have talked about in math class here. If you are relating 2 things together in terms of a graph directly, that means that as volume or as temperature increases, volume is also going to increase, right? So they're directly related, which means if one does one thing, the other is going to do the exact same thing. So if temperature increases, volume also increases. So in this particular case here, guys, this is the new graph we've got here. Volume is the y-axis, temperature is the x-axis here. And now this green line here shows the direct relationship between temperature and volume. So as temperature increases, the y-axis also goes up, which means that we have a resultant that volume is also increasing. So temperature increases, volume also increases. Now, the last one, the last of three here, is going to be something known as a Montan's law. A Montan's law. And this relationship here is specific to temperature and pressure, right? We've talked about pressure and volume. We've talked about temperature and volume. Now we have to talk about temperature and pressure, right? So the last of the three relating to each other, right? The temperature of a gas is also directly related to the pressure. So as temperature increases, pressure is going to increase. So this graph here is going to look awfully similar to our previous one, which is Charles' law, that was relating temperature and volume, right? So the relationship between temperature and pressure ends up being almost exactly the same as the relationship between temperature and volume here, right? They both have a direct relationship. So that means as temperature increases, pressure is also increasing at the exact same pace here. All right, that is what a direct relationship means. Now, we can take all three of these laws here. So if I backtrack a little bit here, we've got Boyle's law, which is pressure and volume, Charles' law, which is volume and temperature, and lastly, a Montan's law, which is temperature and pressure. If we take all three of these relationships here, all three of these, Boyle's law, Charles' law, and a Montan's law, we can combine them together to give what's called the combined gas law. And it's very, very much called the combined gas law because that's exactly what somebody did. They combined all three of those laws, Boyle's law, Charles' law, and the Montan's law, and combined all three of them together to create what's known as the combined gas law. A couple of things though, guys. When it comes to the combined gas law, all measurements of temperature must be in the unit of Kelvin, right? We cannot plug in anything to this formula you're going to see in a second here if it is not in Kelvin. So if you have measurements of Celsius in degrees Celsius, make sure that we use our calculation to convert from degrees Celsius back into Kelvin, and then we can apply them to this formula here. Another thing to note is that if a value is constant, you may leave it out of the equation. Now, that might not quite make too much sense as of right now, but when we do some examples, when I see you guys in class, it's going to make a heck of a lot more sense. So wait until I see you guys in class for that to make a bit more sense. But here we go, guys. Here is the equation. P1 times V1 divided by T1 equals P2 times V2 divided by T2. So there's obviously a lot going on here with this equation. But all it is, guys, is that you're relating to see what happens to the pressure, volume, and temperature of a gas when you change and alter the other measurements. Okay, so you're essentially just seeing what happens to a gas and any of these measurements here, pressure, volume, and temperature, as you change it. And just seeing how those temperatures, pressures, and volumes end up changing from one side on the ones to the other side on the twos here. So it's almost like a before and after picture here. And that's basically all I've got for you guys. So I will see you next time in the next class or video.